Welcome to our channel Circuits Analytica. In this video, we will discuss problems on Thevenin's and Norton's theorem. For the following network, find the Thevenin's and Norton's equivalent of the network connected to 1 ohms resistor. Thevenin's theorem states that any linear complex network except the load resistance can be replaced with an independent voltage source VTH in series with a resistor RTH. Norton's theorem states that any linear complex network except the load resistance can be replaced with an independent current source in shunt with a resistance RTH. To find the Thevenin's and Norton's equivalent, we have to divide the network into two networks, network A and network B. To find the open circuit voltage VOC or Thevenin's equivalent voltage or ISC, first step is to apply superposition theorem, as there are two independent voltage sources, 3 volt and 4 volt. So let us divide the given network into two networks, network A and network B. As it is mentioned in the question that Thevenin's equivalent of the network when 1 ohms resistance is considered as the load resistance. So 1 ohms resistance is network B and rest of the circuit forms network A. Disconnect network B from network A. So hereafter we will consider only network A. For Thevenin's and Norton's equivalent, we have to find Thevenin's equivalent resistance RTH. To find RTH, replace all independent sources with its internal resistance. After replacing 3 volt and 4 volt independent voltage sources with its internal resistance, the network is redrawn as shown. In this network, 10 ohms and 5 ohms resistors are in series. So let us replace this series combination with a single resistance of value 15 ohms. Look at 9 ohms resistance. It is redundant as 9 ohms resistance is shorted. Voltage drop across 9 ohms resistance is 0 as both ends are existing at same potential. That means there is no specific role for 9 ohms resistance in this circuit. So let us remove 9 ohms resistance from the circuit. So redrawing the circuit after removing 9 ohms resistance, we can see a 10 ohms resistance in series with a shunt combination which consists of 10 ohms and 15 ohms. So RTH is equal to 15 ohms in shunt with 10 ohms, which is in series with another 10 ohms resistance. So 15 ohms in shunt with 10 ohms, we will get 6 ohms. Therefore, RTH is equal to 16 ohms. So now according to Thevenin's theorem, we can represent network A as a voltage source VTH in series with resistance RTH. So we have to find the open circuit voltage or Thevenin's equivalent voltage VTH. So Thevenin's equivalent voltage VTH is the open circuit voltage of network A. To find Thevenin's equivalent voltage VTH, let us apply superposition theorem. According to superposition theorem, VTH is equal to VTH1 plus VTH2, where VTH1 is the component of VTH due to 4 volt when 3 volt source is replaced with its internal resistance, and VTH2 is the component of VTH due to 3 volt source when 4 volt is replaced with its internal resistance. So according to superposition theorem, we can write VTH is equal to VTH1 plus VTH2. So VTH1 is the component of VTH due to 4 volt source. So now we are going to find VTH1. In this network, as current flow through the 10 ohms resistance whose one of the two ends is open is equal to 0. So there is no effect of 10 ohms resistance on this circuit. So we can remove 10 ohms resistance from this circuit for the time being. Now if we inspect the output terminals A and B, we can find that VTH1 is nothing but the voltage drop across the 10 ohms resistance. So voltage drop across 10 ohms resistance is denoted as V10B. We can write V10B is equal to I2 into 10. So if we can find I2, then we can write VTH1 is equal to V10B, which is equal to 10 I2. To find I2, apply KVL in the loop which consists of 4 volt source, 10 ohms resistance, 5 ohms resistance and another 10 ohms resistance. Applying KVL for the loop, we will get plus 4 minus 10I2 minus 5I2 minus 10I2 is equal to 0. 4 minus 25I2 is equal to 0, or 25I2 is equal to 4, or we will get I2 is equal to 160 milliampere. Therefore, we can write VTH1 is equal to 10 I2. So VTH1 is equal to 10 into 160 milliampere. So VTH1 is equal to 1.6 volt. Now let us find VTH2. VTH2 is the component of VTH due to 3 volt source when 4 volt is replaced with its internal resistance. If we inspect the circuit carefully, we can say that current flow through the lowermost 10 ohms resistance is equal to 0, as one of its end is nowhere connected. So for simplicity, we can remove 10 ohms resistance from the circuit. In this diagram, as same current flows through 10 ohms resistance and 5 ohms resistance, these two resistors are connected in series. So therefore, we can replace these two resistors with a single resistance of value 15 ohms. So redrawing the circuit, we will get like this. If we inspect the circuit carefully, we can say that VTH2 is the voltage drop across 15 ohms resistance, as 15 ohms resistance is connected between node A and node B. So VTH2 is equal to 15 I2. To find I2, apply KVL in this loop, which consists of 3 volt source, 10 ohms resistance and 15 ohms resistance. We will get 3 minus V10 minus 15 is equal to 0. Rearranging the previous equation, we will get 3 minus of V10 plus V15 is equal to 0, or V10 plus V15 is equal to 3. According to Ohm's law, V10 is equal to 10 I2 and V15 is equal to 15 I2. Therefore, we can write 10 I2 plus 15 I2 is equal to 3. 25 I2 is equal to 3, I2 is equal to 3 by 25, or we will get I2 is equal to 120 milliampere. So VTH2 is equal to 15 I2, that is 15 into 120 milliampere. We will get VTH2 is equal to 1.8 volt. Finally, we will get VTH is equal to VTH1 plus VTH2. VTH1 is equal to 1.6 volt and VTH2 is equal to 1.8 volt. Therefore, we will get VTH is equal to 3.4 volt. So according to Thevenin's theorem, the given network can be represented as a voltage source VTH in series with a resistance RTH, where VTH is equal to 3.4 volt and RTH is equal to 16 ohms. Thanks for watching Circuits Analytica. Enjoy learning.